Sydney. As Sydney said, my name is Juan Carlos Guzman, also known as JC. I think that's for English speakers it's been certainly easier, and that stands for Juan Carlos. That's my two first names. It's not Jesus Christ. Just for that. Just to clarify that. Now, before I start, I'd like to acknowledge the Wajari Jamaji people as the traditional owners of the observatory site where this telescope is located, and also the Noongar people as the traditional owners of this land on where this meeting is held. So the talk is going to be broken into three parts. We're just going to talk a little bit about the overview of the telescope itself. Not many people here know what the ASKAP is, probably. Then I'm going to the main part of the talk, which is a bit of a history, challenges and the future ahead, and some of things I've learned along the path I want to share with you, and mainly for other people who are just doing some other telescope. ASKAP stands for Australian Escape Pathfinder. Is a 36 antenna multi-beam interferometer or radio telescope located in the Murchison Shire, which is, actually Bulari Station is part of the Murchison Shire, which is, if you're not familiar with Australian, West Australian, that matters. So it's about 800 kilometers northeast of Perth, 400 kilometers northeast of Geraldton. Geraldton is the closest town. Nice coastal town in Western Australia, a lot of fishing, mining as well happening there. If you want to go to the observatory, you actually have to, from here you have to fly to Geraldton, drive around 4 hours along the outback. So if you really want to see the outback, that's where it is. And now, why do we build radio telescope in that sort of remote areas? Because of the radio quiet zone. For radio telescopes, we want to be away from all the nice goodies that you enjoy, like digital TV, mobile phones, and Bluetooth, and all that sort of nice wireless goodies. But unfortunately, for radio telescopes, are not good. So that's why we built the observatory there, because just population is almost non-existent. It's a survey instrument. It's primarily built to survey the entire skies, and there's some key science. I'm not a scientist, so I'm probably not going to talk at all about science. One of the key elements of the telescope that makes it a really powerful survey instrument, a very fast one, is what we call the phase array feeds. And I'll have a picture next what it is and how it looks like. Also has a third axis. The whole entire dish rotates to keep the field fixed on the skies as we compensate for the rotation of the Earth. And eventually we're going to do automatic processing. I'm going to talk about a bit later. Currently, we are in the early science mode. We're not fully operational yet. We're in commissioning and early science. Unfortunately, we have a problem with with one of the part of the instrument, the correlator, and we've been just sort of using it in a different mode the last probably 6 months as the engineers trying to fix the problem. And that's a picture of several antennas. Obviously, that one that is pointing to the sky is not working, but the other ones were actually working. So that's the beauty of the ASKAP, which is called the new phase array feeds. It looks like a checkerboard, and it consists of 188 single polarization receivers. So imagine those digital TVs antennas that you have on your roof. One of the novel things of the ASKAP is now the ability to put 188 of them and be able to receive the signals and convert into images. So that also makes ASKAP a really high volume data rates instrument. So what does it mean in terms of astronomical output, wide field of view? So that's the size of the moon. This is the background of the optical image of the Andromeda constellation. That's sort of overlaying the size of the moon. A typical single radio telescope interferometer like VLA, for example, or the ATCA in the East Coast, will look, and you'll need like 12 hours to just be able to image that. However, with the phase array feed, you can do in 12 hours something like that. So it could cover the entire area in one observing. So that one makes the the ASKAP, a very fast survey instrument. This is a nice aerial shot of where it is located. You can see the red, characteristic red dust of the outback, the Western Australian outback. And this is just an aerial photo of some of the antennas. And that just at the end there, the corner, is that the pointer? The central building where the sort of electronics and it's completely shielded room. So we got, we had to construct all the roads, the basic infrastructure. We have 16,000 kilometers of optical fiber, which always just amazed me, how much optical fiber, because out of the 188, you have to connect all of them towards the central site. So this is also a shot of the power station, which is still under construction. I think it's just, they have a quarter of that already in place, and soon will be or full operations. We got one of the largest battery systems in Australia. It was 2.5 megawatt hour capacity, but in a few weeks ago, Elon Musk just made an announcement in South Australia, we're not going to be that anymore for too long. Well, it's 100 days, that's what they say, so we'll see. So this is the system architecture for the ASKAP. So we got basically 36 of this part of it, which is the physical antennas. All of this is happening at the observatory side. So it's 188 cables and all then digitized and sent optically to this central site. So this, up to that point, we have a combined data rate of 20 by terabits per second times, and then it goes to the correlator, which then converts it to 2.5 gigabytes per second. That's what is sent from the observatory to the policy center here in Perth. There is a dedicated optical fiber we've got 4 10 gig links dedicated to that. So all of this part has been part of the ASKAP overall ASKAP project. The ASKAP project has been or has already was funded fully by the Australian government, federal and state government. And again, we're just in the finishing part of construction commissioning, and hopefully we can be full operational next year. So then my specific group starts and gets the data from the correlator, and that's where our responsibility starts. And then my group is being responsible to building the software in particular, and for this side of it. Now, I'm not going to talk too much about, I'm not going to show any formulas. So for everyone what is exciting to see some formulas, then I'm sorry to disappoint you. But just briefly, the radio astronomy problem, in particular, is the imaging is sort of what I call is an iterative. It's not necessarily parallelized. So the idea is, in the case of the ASKAP, we receive some calibrated data. I'm going to explain to. There's something here at the left-hand side that is also important that we have to do. But assuming that is we get the calibrated data, then there's this iteration that happens to produce the imaging. Now, when we start designing the software system for this is 10 years ago, 2 persons that were just part of the team, and they did a lot of the studies of the scaling, they came up with the conclusion that for ASKAP, there are actually 2 things that are dominating the imaging, and it's 90% of the computational cost, and it's called degrading and degrading. And those are the ones that drove the current system that we have today. So the imaging, calibration and imaging software has to produce these 3 sort of products. One is the continuum image, which is very hard to parallelize. It's very iterative. The spectral line is the most highly parallelized because it can parallelize over frequency. We got 16,000 channels of frequency channels that comes from a telescope that we could just parallelize naturally. And this is the transient images, which is more like a streaming, and it has to be done every 5 seconds. So one of the requirements for the ASKAP was to make images in near real time, and all of the 3 types in parallel. So in summary, that there's a lot of already available literature on this gridding and degridding, and in fact we've developed in sort of the end of 2009, 2010, the standalone benchmark in gridding, degridding code. And in fact, I think that's what you can find in the Intel, for example, for the version in the Xeon Phi accelerators, as well as we've got versions for the CUDA, for the CPU, of course, and an OpenMP. So we use that to determine, and it's all explained in that link. You're more than welcome to download. And then out of all of these analyses that we use in the early stages of the ASKAP, decided that what we need is 10,000 cores at 80% efficiency, so it's 4 gigabyte per core. And that's, this is 2009, the lingua franca or HPC, if you're going to go purchase a machine, pick teraflop was the easiest way to actually scope it. So the paper explains that the sort of a transformation from this to what was put as a proposal for the purchase of the machine. So some few numbers that we need to do in ASKAP. So we got 2.8 gigabyte per second coming from the correlator, and that's approximately 10 terabytes an hour. So that's what we need to keep up. And we need to produce images and catalogs, the three types that I showed before, which amounts approximately 5 petabytes per year. And that gets stored forever. Well, not forever, for as long as we can afford it. I think that's probably the best way to put it. At the moment, we actually have up to 15 petabytes total, and we're probably going to have to think about in a few more years to expand that. And those science products at the end is what is get accessed by the community to do post-science analysis. So in 2000, the process started in 2009, but in 2010, it was announced this $80 million supercomputing center called the POSI, and with 25% of the resources will be allocated to the operational requirements. For those of you who haven't visited, you're going to go and visit this evening, the POSI supercomputer. The construction was completed in April 2013. The actual machine for ASKAP was accepted by the end of that year. So what we got for ASKAP is this machine called Galaxy, very appropriate number. It has 2 parts. One is the CPU side of it, which is 472 Cray, I think Intel Ivy Bridge. I'm just looking at Dave. Yeah, thank you. So you notice that I said 4 gigabyte per core was a requirement. We actually got a bit less than that. We didn't go the full 4 gigabyte, which poses a bit of a problem. But we've also got a 1.3 petabyte usable of a shared storage. In addition, we got the ingest cluster, which is a 16 node rack for the ingesting from the correlator, and then do pre-processing before it gets ingested in the compute side of it. So my group's main responsibility has been the application side of it, the software. And that's what we call the ASKAP soft. It's been in development since 2007. And a lot of the design decisions were made during that time. So it is almost like 10 years ago. By then, the current existing code in the radio astronomy was not suitable. We had to reread, so that meant we had to rewrite a lot of the synthesis code. And it's mainly the C++ and MPI. And these are the 3 sort of key assumptions. There's certainly more assumptions, but we assume that the instrument is stable, so then relatively easy to calibrate. Because of this iteration, it does require a global sky model. And also this 90% of computing cost in green, and the imaging model is adequate. Now, all of these assumptions comes with caveats, and the caveat sometimes is the instrument itself. There's some instrumental things that you don't understand that it comes in will sort of, I will say not crumble completely, but it will make sure our life is a bit more challenging. So The other important part of ASKAP software was the ability to make automated pipeline calibration and imaging. If we are going to be able to keep up with the data, we need to move away, and this is a paradigm shift from the astronomer that goes to the observatory, observes, get a DVD, well, this is 10 years ago, then goes back to their institution and then just does all the calibration and the imaging, and it can do it over and over and over again. That's not possible. We cannot store the 10 terabytes an hour. It's definitely not affordable. So that was a key requirement for us to be able to do that calibration and imaging side of it in a one go, in sort of a keeping up pseudo real time, what I call it. However, that was the end goal. That's with full operations, which is not yet there. And during the transition from the moment that we bought we had the machine to the early designs towards now, the whole commissioning of the telescope, of the radio interferometer as it grows, has required different things. The requirements were certainly different to what these automatic calibration. So the other thing that I wanted to know, that the radio astronomy sort of a problem is complicated in the sense that we cover a lot of sort of operational models. I think probably Andreas was going to talk about in the context of SKI. But in the case of ASKAP, you can see the radio astronomy problem first as a streaming application, or you can call it a streaming. This is called the sort of this part of it, the bottom and the hinges. This is something that runs completely real time. The cadence are 5 seconds continuously. And then the other part of it is this middle bit, which is more of a batch job, although automatic has to be triggered and it has to keep up. But then doesn't start until the whole observation has been completed and the calibration has already happened. So we have these two sort of a world that we have to be able to support, the streaming and the batch. And that's certainly for the full ASKAP. However, for the transition period, where we are currently, we got a smaller data set. We don't have all the antennas available. We have less frequency as well, so we definitely have less data. We actually don't understand the instrument very well. We all had assumptions. We have past experience, but the actual having wide field of view instrument like this has been a novel. So one of the requirements that happens halfway through, actually, in fact, it passed the critical design review when we realized, oh, hang on, we need to actually support manual processing. So we had to be able to change a little bit the focus in our development to be able to do this. So create software that is not going to be run or not going to be executed by a machine, in the sense it's not going to be triggered by a machine, but actually going to be used by multiple users manually. So there was no need at this point in time, for processing, automated processing. There was no need for a global sky model, and it's sort of more like a traditional astronomy, but running in a supercomputer rather than in a laptop. So a few results is this is the first 36 beam image produced last year, and you can see, well, it's not, I'm not sure, it's not, I think it's good, but that's the moon, and this is a 36 beam in a sort of a diamond type, and you can see a lot of dots there with the sources. This, I think, took a long, this is 48 megahertz, so it's not 300 megahertz full bandwidth, and it was done again manually. It has a lot of iterations. And this is the other one that it was done late last year for the Spectral Line case. It's the Spectral Line cube of, I think it's 2,000 channels. This is some of the Spectral Line sources. Okay, so changing a little bit in terms of project itself. We are a team of about 7 people distributed between Perth and Sydney. We've done the typical classical radio astronomy project reviews, a preliminary design review in 2009, a critical design in 2010, and last year we have a production readiness review. Note the gap between the 2 years. Certainly it was a bit of a challenge, the fact that during those 6 years between that, things had changed. we follow a iterative software development process, and we use all the goodies, modern software engineering tools that you are all probably familiar with. Issues. I think lately one of the major issues for us, and has diverted a lot of effort, is the fast storage. For two reasons. One is because it's shared, and originally our design was a shared file, global file system, but the sharing was very controlled because it's an automatic pipeline. Therefore, it's only one user writing and one user reading, and we can control the sort of the pattern of usage. However, in the commissioning or during the commissioning period, we have to share this file system with multiple users, which we can't really control what everyone is doing. And the ability also to use other tools to be able to compare to the tools that we're producing. And that poses a lot of problems with the sharing this space with the real-time system. And in addition, we're also sharing with other telescope, our MWI, which is the emergency wide, which we absolutely have no control. We absolutely have nothing to do with the software. So that definitely just impact our non-deterministic performance, and I would like to thank our policy partners because they helped us quite a bit just once this issue was identified, and they actually we were able to move the real-time part of it into another part of another shared file system. However, we still have the issue of sharing this result with multiple users, and that affected the space. And as the last system is getting full, then it started affecting performance, so it's just going into a bit of a problem there. So we recently in May, POSI has procured this new file system to be able to solve this issue, and that has certainly helped us in the short term. I still have probably, due to this fact that we underestimate the amount of space is required for the transition period, we still have a short to support this early science program, which is currently. So the other one is in radio astronomy, there's always a need for this stable instrument to validate, and this is sort of a closed loop between commissioning and computing. And we cannot really validate our software until we get the instrument. So sometimes we have to wait until the instrument is stable before to do that. So it's almost like a chicken and egg. So that certainly has taken a while. The way we do and deal with that is, well, we assign enough effort to be able to support this ongoing commissioning. And like everyone whinge, and I'll have to also whinge because I'm a manager is also sharing resources with other projects is always an issue. Obviously, the third point was we underestimate the effort in this software integration, verification, and support. We always tend to focus and estimate development, but tend to forget the other part that is important. So our next steps at the moment are continue the software development. We haven't finished yet for full ASKAP, so we concentrate on scaling, testing, and debugging. The real-time services in order to support the automated pipelines. We have all the other science pipelines as the basic modes are the continuum and the spectral line, which are two specific science cases. But one very interesting is this one, that we haven't actually completed the full ASKAP yet, and now we start thinking about the upgrade of a Galaxy platform, because usually the cycles are 5 years, so roughly speaking. So we still haven't pushed our software carrying platform, and we have to think about the next one. So we have some time on the new Athena platform recently released, I think, which is cluster of Xeon Phis and another one of GPUs. We're evaluating GPU code. We did evaluate GPU code 10 years ago. Unfortunately, by then GPU was not affordable. The amount of code that we had to just re-implement was huge. So all of that has to feed into this new ASKAP computing requirements for the future upgrade, which I just put 12 to 24 months. I actually still don't know when this is going to happen, which is a bit of a risk for us. Also, we are involved in the SKA as part of the SKA data processor, and we recently got funding from the Department of Industry to continue our involvement along with our partners at ICRA. I think Andreas is going to tackle the SKA tomorrow, but just to give you that the SKA1 low, which is the instrument here in Australia, is going to generate 100 times larger than ASKAP. So it's 2 orders of magnitude more. So what I've learned for this, this is the disclaimer, this is what I learned. I'm not necessarily, like John said, a copyright disclaimer, don't blame me if it doesn't work for you. And this is mainly considering the SKA because it's much more relevant, obviously, coming from ASKAP. But the ASKAP operation model does not follow traditional HPC user support model. I think it's important that, and this is a lesson learned certainly for the SKA or for any radio astronomy that want to incorporate this type of facilities, is the HPC platform now belongs to the observatory. So if the HPC platform is down, my telescope does not work, cannot acquire data because we cannot store, something happened. So being able to keep up, and that poses a lot of new challenges in terms of who supply or who provide you with the service on the platform itself. So one of the things that we've done is build this strong relationship with service providers. So we have the service agreement, but also, and in particular for us, it was very important to be closer to our, in this case, POSI staff, and I think that's helped a lot to build that strong relationship. So whoever is looking after your platform is not your supplier, it's actually a partner, because without their support, your telescope cannot work. So, but there's always room for improvement, and this is sort of my view of if for the SKA, perhaps we maybe to look into dedicated resources at all levels for radio astronomy. And one of the things that happens, at least for ASKAP, is the support we have for computing is sort of a different people to the one that we got for the long-term archives. And perhaps having a more consolidated, dedicated for radio astronomy, more operational for the future, it might be a better model for the SKA. Now, the good thing is we're in a position that whatever we do now will be what the SKA1 likely could be. So we need to take this opportunity to test these things. Commissioning of telescopes takes a long time, significant resource, and is different to the full operation. And for us, was full operation of the telescope. And for us, was so true because we had to divert resources to do the classical commissioning mode. What I've learned is all of this was completely underestimated, and that impacted on delivering the full ASKAP. Isolate the fast share storage, you don't share it. That makes sense. But from the traditional HPC user model, we're actually working with POSI to do that. But John this morning was saying about the storage needs and the SKA in particular. And my advice is, even if we implement POSIT and then we can do all of the stuff with single position, don't and save millions of dollars, but I would say rather than saving, just actually adding to that, include it into more storage, keep the storage as you do because you're going to need it, rather than to slash it by half. Because whatever you estimate today, you probably underestimate it anyway. Does that make sense? Thank you. So are we there yet? I think that's this is sort of my last slide. Look, almost. So we got software working, which is already a good sign. We're actually doing the early science. We are supporting our commissioning group, and we're working towards a full ASKAP. But are we there yet? Not quite, almost. Still lots of work to do. As I said, there's many challenges ahead. We have a new future platform to worry. We have SK also coming along very soon. So, but when software is really finished, I say never, isn't it? Because we're just always changing anyway. Thank you.